I don't know why sometimes if I don't wait for a second from video to video, it just gives me an error message. Okay, one more time. So we are differentiating this with respect to y. E to this function prime is e to the function times the inner function prime, which we already have, times the second function. Now plus the first function times the second function prime with respect to y, but that will be 0. Okay, so then the final form of this is, I'm not going to factor. I can factor 2 and 2 from here. I'm not going to leave it alone. So 2y minus 4 and 2x minus 2 times e to x squared minus 2x plus y squared minus 4y plus 2. And George just lost his right to choose. No, I'm kidding. Okay, so now we want to look at fyx. So when we differentiate this with respect to x, we have e to x squared minus 2x plus y squared minus 4y plus 2 times the inner function prime with respect to y, which we know is 2y minus 4, times the second function, fy with respect to x. With respect to x is 2x minus 2 and times 2y minus 4, and then plus this times this differentiate with respect to x, but it's 0. So obviously the two functions are identical. So we have 2y minus 4, we have 2x minus 2 e to x squared minus 2x plus y squared minus 4y plus 2. The second step of finding the derivatives was cumbersome because of e to this function, but the procedure is the same. Okay, this was step 2. In step 3, we have to create the system fx equals 0 and fy equals 0. Easy to remember because this is how we determined the critical numbers before in chapter 3. Good, so where is my fx? Here's my fx. But when I set this equal to 0, this will never be 0. It's an exponential function, so only 2x minus 2 equals 0. When I set fy equal to 0, only 2y minus 4 can be 0, because this is never going to be 0. E to a function is never 0. Good. That's really nice. Look at this. This is our system. X equals 1, y equals 2. Wonderful. So the critical point is 1, 2. So we determined all 6 derivatives. I checked fxy and fyx are indeed the same. Very important to check. Because if they're not the same, something went wrong somewhere else in the process. Then we found the critical point, which is 1, 2. At this point, we need to calculate the d-test, so-called the number d. If it's positive, negative, or 0. So step 4, d. Remember, it's fxx at 1, 2 times fyy at 1, 2 minus fxy at 1, 2 squared. Okay, fxx at 1, 2, fyy at 1, 2 minus fxy evaluated at 1, 2 and squared. Okay, so we have to be careful here when we plug in 1, 2 in fxx and then in fyy and then in fxy. Okay, so here's what happens when I plug in. Let me show with a different color. So this is fxx. But when I plug in 1, 2 minus 2 is 0. This whole thing goes away because 0 times this is 0. So I only need to plug it in here. Of course, 1 and 2. So 1, 1, 2, 2. Because this portion is 0. So let's see what we get. So fxx at 1, 2. This is just algebra. So this goes away. So then I have 2 e. So let's see, x squared, 1 minus 2 plus 4 minus 8 plus 2. So x squared is 1. Negative 2 times 1 is negative 2. And then I have 2 squared, which is 4. And then I have negative 4 times 2, which is negative 8. And then plus 2. These two go away. So this is 2 e to negative 3, which is 2 over e to the third, which is positive. Okay, I'll go back and put them in, but now I have to determine fyy. With fyy, when I plug in 2 here, this will go away. So I only need 2 times the same thing, e to negative 3. So this is also 2 over 3, 2 over e to the third, which is also positive. Finally, we need to find fxy. But here's what happens. When y is 2, but that's what it is, this is 0, this is 0, the whole thing is 0. Nice. So therefore, from here, I jump over here, and I put 2 over e to the third times 2 over e to the third minus 0. Obviously, this is a positive number. I don't care to even calculate it. I only need to know whether d is positive, negative, or 0. So d is positive. Now I look at this number. Because d is positive and fxx is also positive, what do we conclude about 1, 2? D is positive and fxx is also positive. What do we conclude about 1, 2?
Relative max.
Yeah.
Minimum.
Yeah, relative.
So let's go back. So let's analyze this one more time. How do you remember? Is like, remember x squared? If x squared has a negative leading coefficient, it's a maximum. If x squared has a positive leading coefficient, it's a minimum. So if d is positive and fxx is positive, there is a relative min. If d is less than 0, nothing. If d equals 0, or the saddle point, if you want. If d equals 0, the test is not applicable. Okay, let's choose another. Only because this one was a very good exercise. Thank you, George. But it was a little bit cumbersome to follow. And the fxx and fyy. So let's choose another. This is obviously not a problem for the test. It's too long. You will have a problem like this, but not to fill up 3 pages to find fxx and fyy and fxy. No. I don't want to torture you. I just want you to understand the basics of how to find a relative max, relative min for a function of 2 variables. Okay, so let's choose one more and go through that. Those steps, all steps again.
Can we do 10?
Yes. Let's take a look. Where is 10? I see it. So fxy is x squared plus y squared plus 8x minus 10y. Perfect. Good. So we have 6 derivatives to find. fx, fxx, fy, fyy, and fxy, and fyx. Oops. Good. We differentiate with respect to x and only with respect to x. What do we get?
X plus 8.
Very good. 2x plus 8. Let's also do the fxx. What do we get?
Just 2.
That's it. Nice. Easy. Good. Fy.
Two y minus 10.
2y minus 10. Fyy.
Two.
Good. Fxy. Fx with respect to y.
Zero.
Exactly. Fyx with respect to x. They have to be the same. Otherwise, we have an error somewhere. Fyx,
Zero.
0. Perfect. Now we have to create a system. The system is fx equals 0 and fy equals 0 because we need a point. So we have 2x plus 8 equals 0 and we have 2y minus 10 equals 0. Can anyone give us the point for this problem?
-4 and 5.
-4 and 5. Very good. At this point, we determine the d value or d test. And we have fxx at -4, 5 times fyy at -4, 5 minus fxy evaluated at -4, 5 and squared. But fxx is just 2 and fyy is just 2, so this is 4. And fxy is 0, so this is a positive number. So fxx is positive and d is positive. What do we conclude about -4, 5? It gives, again, a relative min. What I forgot about to do in the previous problem is we have to find it. So it's not sufficient to say, oh, it gives a relative minimum, but we have to find it. Meaning we have to go back with the point, back to the original problem and determine the actual minimum. So let's do it for this problem. So I have to find f of -4, 5. So -4 squared is 16. 5 squared is 25. Minus 32. And then minus 50. So this is -16 and minus 25, and this is -41. So -4, 5 gives a relative minimum, but the actual value, the actual minimum is -41. I would like to show the very last section of this chapter and the last section of the course, and then we'll go back and work on a word problem. So we have word problems, maximizing this, minimizing, whatever. So I want to come back to this, but I just want to show you the very last section, which is only a calculator step by step. 582. Okay, so I have it ready. I just want to explain what it is. So the last section is called linear regression. And the question is, why is linear regression in this class? And what does it mean? Okay, so imagine, let's say I have 10 students, and I'm going to measure your height, and let's say blood pressure. Just two variables. I'm going to measure your height and I'm going to measure your blood pressure. So for each and every one of those students, I have x comma y. Height, pressure, blood pressure for student 1, for student 2, and so on and so forth. Here's what I do next. I create a scatter plot. X is on the x-axis, y is on the y-axis. Of course, this is the height and this is the blood pressure. And I create a cloud, so to speak. I put the points for each and every of my students. And let's suppose the cloud looks like this. It's not cloud, it's a scatter plot. Let's say it looks like this. Let's say it looks like this. From all these 3 examples, only for the first example, I can fit the line of best fit. The line with the minimum possible error, because the scatter plot looks like a tendency of a line. This one is quadratic. This one has nothing to do with linear regression. This one appears to be exponential, has nothing to do with linear regression. This one is the only one in my 3 examples that follows a straight line situation. This one with a positive slope. It can be with a negative slope. Something like this. All we want to do is here, and you can say, okay, well, where is the calculus part? Well, the calculus part that the calculator will do for us is in minimum error. Every time we talk about minimum, we talk about calculus. But we don't have to do anything because the calculator will determine the line of best fit for us. Okay? So in my example, you could say, well, you can fit this line. Okay. Or you can fit this line. Okay. But this one is the best. The best fit, the minimum error. Okay. The minimum error. And the calculator will determine for us the line of best fit. Here's how. So, hourly wage. The minimum hourly wage in California has grown over the years as shown in this figure. 0, meaning in 2014 it was this. In 2016, 2 years later, it was this. 3 years later, in 2017, and so on and so forth. For the data in the table, find the regression line. Regression line means the line of best fit, the one with the minimum possible error. And it's a line, y equals mx plus b. Use this regression line to predict the minimum hourly wage in 2022. by 2024, the minimum hourly wage in California will be this. Is the estimate of this future value provided by the regression line accurate? So when we look at the data is somewhere between 2014 and 2019. 2019 was exactly before the pandemic, right? So we never know how far out I can use the line. What do I mean by that? So here's the line of best fit. So let's say this is between 2014 and 2019. But if you ask me to use the line and predict, because that's what we are trying to do, we're trying to determine this line that predicts. If you ask me too far out, I'll say, I don't know if the trend continues. This may be out of the range. Maybe 2022 will not be that bad, but maybe 2030, something may change and the line may not be accurate anymore. Too far out. Okay, so first of all, I would like to record this, although I have it recorded. If you want me to record it now, I can, but I will wait for you to turn off your cameras because I don't want to record anybody. Okay, so I'm assuming that you want me to record it. I will record it. Good, so let me... Okay, before I share... No, I want to do it after I share. Okay. Okay. So in the graphing calculator, I am going to enter the data as you see here exactly as it is presented, 0, 9, 2, 10, and so on and so forth. Here's how we do this. So we start with statistics, stats, and we edit. I clear my lists. Clear after I highlight the top of the list, the name of the list, the label, clear. And then I go back and I put them exactly in this order, 0, 2, 3, 4, 5. 0, 2, 3, 4, 5. So I have the first point, 0 this, 2 this, 3 this, 4 this, 5 this. These are my points. 9, 10, 10, 50, 11, and 12. 9, 10, 10, 50, 11, and 12. I'm checking. 9, 10, 10, 50, 11, and 12. Good. I have the data. Then I go to stats. Or you can second and quit. Go to stats. And now we want to perform calculations. All we want is number 4, the linear regression, where A is the slope of the line and B is the y-intercept. So I click on 4. Make sure that you have list L1 as X, second list L1, and list L2. And I would like to store the regression line. I don't want to punch it in myself. I want to store it where? Click on variables, variables again, function, and I want to choose y1. So I want the calculator to create, to use list L1, use list L2, and create the linear regression line of best fit, and also put the function in the graphing calculator under y1. So now I calculate. It calculates. It gave me the regression line, which is y equals the slope 0.5743, x plus b, which is 8.8919. Now, I get out of there and I look at y equals. The function is there with as many digits as possible, which I would have never done to put it in myself. One other thing before we look at the graph, one other thing I wanted to show is this. When we go to second and stat plots, I would like to graph the data I have. I would like to see the cloud, so to speak, the scatter plot. So I click on enter. I want to highlight, I'm going to turn this on. Yes. The first symbol is the scatter plot. X is the listel 1, Y is the listel 2. I want the blue color, I want the square, or you can put this cross, the dot, whatever you mark you want. And I want to see it. But I want to make sure that I'm using the correct viewing window. Because remember, X is between 0 and 5, and Y is between 9 and 12. I want to adjust the viewing window accordingly. So I go to the window, and 0 to 10 is fine. Scale of 1 is fine, although this could be just 6. Y minimum, why would I want to see 0? Because it starts at 9, so below 0 there is nothing. Okay, and the maximum goes to 12, 13, I can put 15 with a scale of whatever, 3. I want to see that this is indeed, that has a linear tendency. Does it? Yeah, look at that. It does. And here's the line. Which line? This one. So it created both the scatter plot and the line of best fit. And I see it. Now, the next question here was, use the regression line to predict the minimum hourly wage in 2022. But 2022 is 8 years since 2014. So all I need to do is go back to the second table and put in 8. So it appears that if the trend continues, I don't know if it did, the minimum hourly wage in 2022, it appears to be a Y equals the predicted, it's called Y hat, 13.49. So use the regression line, the prediction, right? So Y hat to predict the minimum hourly wage in 2022. By 2024, the minimum hourly wage in California will be this. Okay, so I'm going to plug in this case, 10 years and see if I get 15. But again, you can say, well, do you guarantee that the trend continues? Because if you do guarantee, then it's okay. So the trend was not exactly 15. It didn't give us exactly 15. Okay, it gave us 14.63. So the predicted for 2024 was not the accurate 15, was 14.64. Why? Because the range of data is between 2014 and 2019, and 2024 is a little bit out of the prediction area. Is the estimate of this future value provided by the regression line accurate? No, not really. It's not that far, but it's not 15. That's all we need in 6.4. So you just have to enter the information in the graphing calculator. The calculator will give you the linear regression line, and you will be asked to predict the values using, this is what is called the predicted. I use the prediction. Of course, this is the line that the cloud, the scatter plot gave us. But the prediction may or may not be on the money as we speak, as we say.